Hello, in this video I will be discussing the mechanisms of the 5 electrophilic aromatic substitutions that we talked about in the last video. The mechanism for all 5 reactions is pretty much the same, at least the key steps in the mechanisms are all the same. It's how we form the electrophile in each case that matters. So what I'm going to do first is give you a generalized mechanism, and then we'll see how each of the 5 individual reactions varies. I will draw the electrophile, and that represents any one of a number of different actual molecules with a positive charge, depending upon whether we're talking about nitration or halogenation or one of the Friedel-Crafts reactions or sulfonation. That's a different thing, but this is a generalized symbol for several different molecules. And if we react it with a benzene ring having a hydrogen, and I've drawn the hydrogen off to the side a little bit here just to make room for the electrophile, and if we draw a pair of electrons out of the benzene ring, I'm using that pair from the benzene ring, double bond, put it in here between the electrophile and that carbon, the net result of that step is that both the hydrogen and the electrophile will now be attached to that carbon. Notice that that's now an sp3 hybridized carbon. It's tetrahedral, and in fact this intermediate is sometimes referred to as the quote tetrahedral intermediate, otherwise known as a Weyland intermediate. That's WHELAND, named after the person who proposed this mechanism. Notice that when we pull this pair of electrons out from the bond, that leaves the carbon next door with a positive charge. And now notice that that step is really exactly like if we add an H plus to a regular alkene double bond, you end up with a positive charge on the carbon next door. Or if we add an ER plus to a conjugated alkene, we end up with a positive charge. And those are actually electrophiles as well. So this electrophilic idea is not really new, it's just we haven't used that word for it. These 2 bonds in the benzene ring remain as double bonds. And so what we end up with is a molecule which has now lost its aromaticity. Notice that this is no longer aromatic. In fact, it's not conjugated all the way around, so it's not aromatic or anti-aromatic. But it is pretty stable because notice that it's conjugated with this double bond and also with this double bond. So you can draw 2 more resonance structures for that. It's a pretty stable molecule. In fact, let's just go ahead and do that. Let's draw 2 more resonance structures for that. What we're going to do, and this will be a very important skill because we're going to have to draw resonance structures a lot in this chapter, including these basic kinds of resonance structures. Let's first consider taking this pair of electrons and moving it up to there, and that's going to leave that carbon positive. And then a third one in which we will move this pair of electrons down to there and leave the positive charge at that position. Now, very important idea. Remember, when you're drawing resonance structures, you cannot move atoms. So the hydrogen and the electrophile remain attached to that carbon. You can't move around to different carbons in the benzene ring. Each of these 5 positions has another group, perhaps a hydrogen or perhaps something else, but whatever those groups are attached to these 5 carbons, they remain, each of them attached to those 5 carbons in each of those other resonance structures. So we haven't moved any atoms, all we've done is move the positive charge, and notice that the positive charge can end up on this ortho carbon to where the electrophile attacked, this ortho to where the electrophile attacked, or this para position to where the electrophile attacked. Never on the meta position. And you can try, but you will find that you can never draw a resonance structure in which the positive charge ends up meta to the position where the electrophile attached. I recommend that you try to draw a resonance structure with a positive charge here, move the double bonds around, and you'll find that you can't do it. Remembering that there has to be one other bond at each of these 5 positions, but only one other bond there, nothing, just one group attached at each of those positions. So this is the key step in electrophilic aromatic substitution. The electrophile attaches at a position where there's a hydrogen, and then you have an intermediate called the Weyland intermediate, which will have at least 3 resonance structures. Okay, the 3 that we've drawn here, plus in some cases some more, but for now just those 3 resonance structures. Then the next step that happens in the mechanism is that Weyland intermediate, which I'm going to redraw down here, and I'm going to draw the first of the 3 resonance structures, that's this one. But notice that you could draw the second or the third resonance structure, and it would work also in this step. But basically what we're going to do is drop this pair of electrons that's holding the hydrogen on into that position. So this pair of electrons moves into there. That leaves the electrophile still attached, but restores the double bond in that position. So there's the double bond restored. We now have our benzene ring restored. Our aromaticity is back again. That's a good thing. But now the electrophile is attached. Okay. What else has to be there? Well, the H plus has to come off. So we'll write it over here as H plus. But remember, it's really not H plus. It's actually coming and becoming attached to whatever's pulling it off. Some sort of base has to come in and pull off that H plus from the molecule. We'll see what that base is when we do each of the individual 5 reactions for the electrophilic substitution. But these are the 2 main steps in electrophilic substitution. First, the electrophile adds to form a Weyland intermediate, and then the H plus gets pulled off to reform the benzene ring. Now think about this. Even though this is a pretty stable carbocation, it's not nearly as stable as the starting material or as the product, which means that it takes quite a bit of energy to get to this position because 2 reasons. First of all, you're forming a carbocation, and that's hard to do. And secondly, and probably more importantly, you're breaking up the benzene ring. So you have, remember, the extra added stability of the aromatic ring here and here, but not in between. So it's like you're starting at very low energy, you have to go up to a big intermediate here, and then go back down to the final product, which is again a stable molecule. That means you need some pretty severe stuff going on in order to get over that energy barrier, and that's why we need concentrated sulfuric, concentrated nitric, and those other strong Lewis acid catalysts that we saw as the actual reagents. So that gives us an idea of why it happens, why it needs such severe conditions. Okay, now let's look at the individual mechanisms. So first, let's consider nitration. And here is the overall balanced equation. Here's the benzene ring. We're going to add nitric acid on the left-hand side of the arrow. Over the arrow, we're going to write the sulfuric acid. As it turns out, the sulfuric acid is a catalyst in the mechanism. It's not actually part of the balanced equation. And we'll end up with a hydrogen having been replaced by a nitro group. And what else? What else do we need to balance the equation? Well, one of the oxygens from here is gone. That hydrogen is gone, and that hydrogen is gone. So as you might have guessed, we will get water as a byproduct. Okay, so there's the balance equation. Here's the mechanism. It's going to turn out the first 2 steps are simply inorganic stuff. The benzene ring doesn't actually enter into it till the 3rd step. So the first step is that the nitric acid, which I'm now going to write as HONO2, which hopefully that's okay because nitric acid is in fact a nitrogen with 3 oxygens and hydrogens attached to one of the 3 oxygens. So this is just a little bit more informative way of writing nitric acid than that one is. And we're going to react it with sulfuric acid. What we're going to do is a simple acid-base reaction where the sulfuric acid is going to get to do what it wants to do, which is to be an acid, and the poor old nitric acid is going to have to act like a base. Nitric acid does not want to be a base, it wants to be an acid, but it's actually a base in this reaction. So the H plus is going to protonate that oxygen right there. We'll end up with this odd-looking intermediate in which the nitric acid now has a positive charge on a nitrogen, just protonating that oxygen, just exactly like you protonate an alcohol, kind of makes sense. And the byproduct, or the counter ion if you will, is the bisulfate ion, F, which is the conjugate base of this acid. Okay. Then what happens is that the protonated nitric acid, being extremely unhappy, having that proton attached to it, just kicks out the water. So water gets booted out, and that's where the water comes from in the final equation. So we get water plus NO2 positive, and it's the NO2 positive that's the actual electrophile. Okay. We drew a strong Lewis dot structure for it just to remind ourselves. NO2 positive has a pretty good, easy to draw Lewis dot structure. Everything follows the rules. The nitrogen only has 4 valence electrons, so it has a positive charge, but everything has an octet, so that works out just fine. Now we get the third step, and this is the same as the first step I showed you a minute ago, where the electrophile actually attaches to the benzene ring. So I'm going to draw it this way. Here comes the benzene. And these last two steps will look familiar to you because we just did them. And here comes the electrophile, NO2 positive. Because that's a positive charge and it loves electrons, thus it's an electrophile, it pulls a pair of electrons out of the benzene ring, forms a new bond in there, and we get the famous Weyland intermediate with its hydrogen and nitro group both attached to the same carbon. The other two double bonds are still there. And remember, you can draw two more resonance structures for that Weyland intermediate. Certainly I would recommend that you draw them. I'm not going to draw them now just to save time. And then the fourth step in the mechanism is that Weyland intermediate loses its H+. Oop, too many double bonds. Positive charge there, hydrogen, nitro group. This is going to lose its H+. So what does it lose it to? Something has to come in to pull off that H+. In the general mechanism I showed you a minute ago, we just had it pop it off as H+, but of course something has to actually pick it up. What do you suppose it is that picks it up? That HSO4 minus that's been hanging around the whole time, balancing out the positive charges in each case. So we're going to bring back the HSO4 minus. It's going to pull off that H+, and we will end up with our balanced equation. Nitro on the benzene ring, and H2SO4. And therefore notice that the H2SO4 is regenerated, ready to go back and do the first step again. Thus it's a catalyst, it's not actually part of the balanced equation. Okay. That's the nitration reaction. Now let's look at the sulfonation reaction. Here's the balanced equation for sulfonation. Benzene ring with hydrogen, and the reagent is going to be the SO3 part of the fuming sulfuric acid. So the SO3 is actually the reagent, and again the sulfuric acid is simply a catalyst. Okay, so it's going to be in the mechanism, but it's not going to, it's going to come back out again at the end of the mechanism. And the product is benzene sulfonic acid. And notice then that we don't need a byproduct because the hydrogen that comes off here can be thought of as being that hydrogen right there. Whether it's actually the same proton or not is another question, but at least the balanced equation is complete. We don't need a byproduct. Here's the mechanism. Again, the first step here is simply going to be an inorganic reaction in which we will be preparing the electrophile, and then we will get that key step where the electrophile reacts with the benzene ring. But the first step is simply that the SO3 here reacts with the sulfuric acid. And again, the sulfuric acid does what it likes to do, which is act as an acid, and it donates a proton to the SO3. So we're going to protonate the SO3, and it's going to become SO3H with a positive charge. And the H2SO4, of course, ends up as a SO4H minus. So that's a bunch of S's and O's and H's and charges. It's easy to get lost here, but this is SO3H because we've essentially added a hydrogen to SO3, and it ends up being positive. And HSO4 negative is the conjugate base of this acid, so that makes sense. Just to be clear, let's go ahead and draw the Lewis dot structure for SO3H. Sulfur, double bond O, OH, positive on sulfur. Okay. At least that's a possible Lewis dot structure for it, and there may be other ones. You can draw resonance structures for it, but essentially that's the easiest one to think about as going on in the next step. So now we have the electrophile prepared. That is in fact the electrophile, and it's ready to attack the benzene ring. So here's the benzene ring. Here comes the SO3H positive. We pull a pair of electrons out, form a new bond between the sulfur and the carbon, and we end up with the famous Weyland intermediate with the hydrogen and the SO3H and a positive charge next door because that pair of electrons is no longer there, so that carbon ends up being positive. And then of course in the third step we lose the H+. So here's our molecule with the hydrogen and the sulfonic acid group, both on the same carbon and its positive charge. We have to pop this H plus off of there. What is it that's going to pick up the H plus? Again, it's the HSO4 minus. So we end up with a sulfonic acid group on there, and H2SO4 is regenerated. Okay. That's the sulfonation reaction. So you can see nitration and sulfonation, the mechanisms are pretty similar. One difference is that it only takes one step to prepare the electrophile in the sulfonation reaction, whereas it took 2 steps to prepare the electrophile, that NO2 plus, in the nitration reaction. Let's move on to a third one that's a little bit different from the first two, and that is the halogenation reaction. In this reaction, the benzene ring with its hydrogen reacts with, and I'm going to use Br2 as the reagent. Keep in mind it could also be Cl2, not iodine and not fluorine, but Br2 or Cl2 will work. And over the arrow we're going to write FeBr3, and we're going to end up with the bromine attached. And what would the byproduct be, if any? Hydrogen from here and one of the 2 bromines from there. So we get HBr as the byproduct this time. Okay, here's the mechanism. First step, the Br2, and I'm going to draw it out, Lewis dot structure wise, reacts with the iron tribromide. And the iron is very electron deficient. In other words, it's a Lewis acid. If you remember from our discussions of acids and bases first semester, Lewis acids are those things that want to get electrons towards themselves. So it sees one of these pairs of electrons on here and it says, okay, I'm going to bond with that pair of electrons, and it's going to form that very strange looking thing, in which the bromine has a positive charge because it's used one of its pairs of electrons to form this bond. And iron has a negative charge because it's picked up an extra electron that it didn't have before. So it's a very strange looking intermediate. Now in the book and in some sources they will say that this then goes on to form Br positive, which you actually end up with a standalone positive bromine. This bromine donates electrons to that bromine, and you end up with FeBr4 negative and a positive bromine ion. Now I don't think that's really true. I don't think you actually end up with a positive bromine. I think it actually remains attached to this, and then in the next step when we are going to attach it to the benzene ring, it's actually that whole complex that attaches to the benzene ring. And I'm going to show you how that works. Here's the bromine on the end, here's the positive bromine, here's the iron. And then the other 3 bromines, negative, positive. This pair of electrons gets pulled out to form a new bond with this bromine. And then this pair of electrons drops in to satisfy the positive charge on that bromine, and you end up with FeBr4 anyway. So whether it's this whole thing that reacts, or whether it's actually a Br plus that's a standalone ion attaching to the benzene ring, really doesn't matter, because you get the same result anyway, and that is that you end up with a Weyland intermediate in which you have both a hydrogen and a bromine attached to that carbon. The one next door ends up being positive because it's had its pair of electrons pulled away from it. And you end up with a molecule in which you can draw 2 more resonance structures, just like in the previous 2 mechanisms. And you end up with FeBr4 negative as a counterion for that positive charge on the Weyland intermediate. And then the last step in the mechanism, that Weyland intermediate as its H plus pulled off. So what is it that pulls off the H plus in this case? Well, it's really the FeBr4. We'll write it as plus FeBr4 negative. And it's one of those four bromides that picks up the hydrogen and becomes the HBr. So we'll end up with the benzene ring restored with its bromine plus HBr plus FeBr3. And then the FeBr3 is ready to go back and restart the first step. So again, it's a catalyst and it's written with an arrow because it goes into the mechanism here and comes back out of the mechanism there. I know that's a little bit more complicated than the other two mechanisms, which are much more straightforward and easy to remember. If you want to write it this way, where you first form an initial Br plus, that would be okay. I would accept that. If you want to write it this way, as I have, in which it's actually this whole complex that reacts with a benzene ring, that's okay too. It really is 6 1/2 dozen of the other. Let's go on and look at the Friedel-Crafts reactions now. So, Friedel-Crafts, and I'm just going to use FC for the abbreviation, alkylation. Here's the overall balance equation. Benzene ring with its hydrogen plus alkyl halide. I'm going to use Rx, and again that can be chlorine or bromine, with aluminum trichloride as the catalyst. Forms an alkyl benzene plus HX. And again, that could be HBr or HCl. So we have a balance equation. And as mentioned in the previous video, the R group may or may not be rearranged here. If it's a carbocation that could rearrange, then it will rearrange. And we'll see here in a minute how that happens. First step, the alkyl halide reacts with the aluminum trichloride, much the same way that bromine or chlorine reacts with FeX3. In other words, that X is going to end up attached to the aluminum, and the R group is going to end up being positive. Or saying it another way, this aluminum essentially abstracts an X minus from the alkyl halide, and you end up with a good old-fashioned, full-fledged, positive carbocation, just like we saw in several reactions in the first semester. And the byproduct there will be XAlCl3 negative. If X happens to be chlorine, then that's AlCl4 negative. If X happens to be bromine, then it's a mixed aluminum halide, and you end up with 1 bromine and 3 chlorines attached to aluminum. So this is then a carbocation. Now, you may have another step in here in which the R group rearranges. Perhaps, let's put that in there. And you know already how to predict whether a particular carbocation will rearrange. If it can become secondary from primary, or if it can become tertiary from secondary by shifting a hydrogen or shifting a carbon group over, then that will happen. So we'll just leave it at that for the moment. And then in the second step, or possibly third step, if there's a rearrangement, then this becomes the third step because that's the second step. The R plus reacts with the benzene ring. So the benzene ring with its hydrogen comes in. Here's the R plus, that is the carbocation. It pulls a pair of electrons out of the benzene ring and produces, again, the Whelan intermediate, in which you can draw 2 more resonance structures. Plus, well, that's it. You just form the carbocation, and again, you can draw 2 more resonance structures. Then in the last step, which will be the third step, unless of course there's a rearrangement, in which case that becomes the fourth step, the H plus is going to have to be abstracted. Where does that H plus end up attaching to? It's going to take the AlCl3 negative, and it's going to, that X is going to go with that hydrogen, and so we'll end up with the alkyl benzene plus HX plus AlCl3. And that's the overall balance equation then. So again, it's basically the same mechanism, it's just that we take 1 or possibly 2 steps to prepare the electrophile. The electrophile then reacts with the benzene ring, and we have the same two key steps always in these reactions. Now let's look at Friedel-Crafts acylation. Very similar to this mechanism. The only difference is going to be what the carbocation looks like. So this is Friedel-Crafts acylation. Overall reaction, benzene with its hydrogen plus an acyl chloride with AlCl3 produces a ketone plus HCl. And here's the mechanism. First step, the acyl chloride reacts with the aluminum trichloride in exactly the same way we saw in the previous mechanism, and also essentially the same way we saw with the FeCl3 reacting with Cl2 or Br2, and you end up with a positive charge on that carbon. In other words, a carbocation, positive charge on there, and the AlCl4 negative. Okay. Now, how do you like that carbocation? By the way, this is called an acylium ion. That's ACYL-IUM, not SILL-IUM. It is, although it's acyl cation, it's the acylium ion. How do you like that as a positive charge? Well, it doesn't look very good to me as it is, but again, there's another resonance structure for it. You can draw this ion, remembering that there are two pairs of electrons on that oxygen. One of them can come down and help satisfy that positive charge. That gives us a triple bond and a positively charged oxygen. So these two constitute a pretty good carbocation. Okay? And then it's that attacks the benzene ring in the next step. So here we go. Here comes the benzene ring with its hydrogen, and the rest of it is pretty much like we've seen before. Here's the acylium ion, and I'm drawing it in that resonance form, although that resonance form is actually the better one because everything follows the octet rule in that resonance structure, but not that resonance structure. I'm still going to draw this one simply because it's easier to see what happens next. And that is that pair of electrons moves up into there, forms a bond between the carbon and the carbon, hydrogen and acyl group, positive charge there, and we have the famous Weyland intermediate again, two more resonance structures possible, and then in the last step, we just pop off the H plus and it goes where it has to. Which is, it goes on to one of the chlorines from the AlCl3, so we're going to bring, or AlCl4 negative, so we're going to bring that in. One of these chlorides is going to pop off and go with that hydrogen. So the acyl group is still attached there, the benzene ring is restored, HCl is produced, and the original AlCl3 is reformed, ready to go back and start again. So thus it's a catalyst, and that's why it's drawn over the arrow. So there you have it. Those are the mechanisms for the 5 main reactions that we call electrophilic aromatic substitution. Thank you for your attention.